In this video, I'm going to prove that the square root of 2 is irrational. Now, remember from class we proved that if b is an integer and b squared is even, then b is even. Okay, we're going to use that fact in this proof. Now, one thing that we're also going to use is that every rational number can be written in lowest terms. So, for example, 15 over 20 is certainly a rational number, but it's not in lowest terms. Lowest terms would be 3/4. So that's a fact we're going to assume is that every rational number can be written in lowest terms. All right, now to prove that the square root of 2 is irrational, we're going to do a proof by contradiction. Okay, so we're going to assume, by way of contradiction, that the square root of 2 is rational. Okay, it's a rational number. Okay, and what this means is that we may write the square root of 2 is equal to p over q, where p and q are integers. Q is not equal to 0, and p over q is in lowest terms. Okay, I hope you can read my writing here. Okay, so if the square root of 2 is equal to p over q, then we can square both sides of that equation. Okay, and if we square both sides of this equation, we get this. Okay, so 2 is equal to p squared over q squared. Okay, thus 2q squared is equal to p squared. Okay, now what this shows is that p squared is even, because p squared is 2 times an integer. Okay, so p squared is even. But if p squared is even, then p is even. Okay, that's the fact that we proved in class. Okay, thus p is equal to 2k for some integer k. Okay, that's what it means to be an even numbers, that it's equal to 2k for some integer k. Okay, now let's go back up to our equation here, 2q squared equals p squared, and let's plug in 2k for p. Okay, so we have 2q squared is equal to p squared. Okay, but p, remember, is 2k, and so what we have is 4k squared. Okay, so we have 2q squared equals 4k squared. Okay, dividing both sides of this equation, 2q squared equals 4k squared, by 2 gives that q squared is equal to 2k squared. Okay, now what this tells us is that q squared is even. Okay, but because it's equal to 2 times some integer. Okay, but again, if q squared is even, then q is even. Okay, now this is actually a contradiction, because p and q are both even. Okay, since p and q are both even, okay, we have a contradiction of the fact that p over q was in lowest terms. Okay, if p and q are both even, then p over q can't be in lowest terms, because you could divide both the numerator and the denominator by 2. Okay, so therefore, what was wrong? Therefore, what was wrong was our original assumption that the square root of 2 was rational. Okay, so therefore the square root of 2 is irrational. Okay, so this is an example of a proof by contradiction.